So first, I'm very glad to be virtually here. I apologize that I cannot come. It seems that CNRS doesn't like, the Lufthansa doesn't like CNRS, or they both doesn't like me, or whatever. But I was refused boarding. There are no ticket in their system. So, but let me try online. And I'm still very happy to see you and see Yuri even in this reduced way. So I guess you all heard about Kolmogorov complexity. It all came from the first paper, which was called Three Approaches to the Definition of the Amount of Information, три подхода к определению понятия количества информации in Russian. And they, in this paper, they said that how to measure information. We should consider the minimal length of the program which produces some object. And of course, it depends on the choice of this programming language or interpreter of its language or decompressor. And we want this to make the function minimal. And there are many. Kolmogorov noted that there are many, there exists some U which make this function minimal up to a constant, but there are many of them. And then natural question, what he already asked, whether one can choose some right one. And he said, and this is mostly what we think now, that it's not clear how to make this choice, and we can have different possibilities going from some natural programming language, common programming language, and a bit hundreds of bits is still looks a bit optimistic. We will see it later, but still for War and Peace, it's long enough to make this quantity meaningful. So this was but it's interesting to see what different people thought at how they tried to choose this U. What were the attempts to fix some U or consider some class of this U as maybe some more precise class, not consider not all optimal use, but only some optimal use. So what happened later? And first, actually, it was not even later, it was a bit before. There was a paper of Solomonov a year before, and even earlier papers in technical reports, but probably nobody have read them before Kolmogorov, but still he decided that you should consider not just optimal U. He did not have this notion of optimality, but he said that we should consider a universal machine. A universal machine means that it can simulate any machine in a very specific way. You just need to add some prefix. Here is alpha. We need to add some prefix, and if we fix this prefix and then put the thing in the universal machine, it should behave as our arbitrary machine without this prefix. So it's a translation instructions or program that is interpreted and so on. And this is a stronger property. You can easily construct artificial examples of optimal machines that are not universal, but still any natural construction of a universal optimal machine really use universality. And then the natural question is, how should we define complexity? Do we need a universality, or it's just enough to have optimal things? This is a bit of a theoretical question, just because we don't know any natural optimal construction without universality, but still. And it's interesting to see historically what was in the main text sources about Kolmogorov complexity. So Chaitin defined in 1999, he wrote a paper when he considered just very specific universal machines. And in his previous paper of 1966, he didn't consider real Kolmogorov complexity. He has some considerations in terms of Turing machines, number of states, and so on. And the most famous textbook is Lee and Vitani, which is kind of unclear about this. So in the last edition, they say just fix an optimal universal machine. But optimal machine is defined, but universal machine is never defined in this book, in this edition. But in the second edition, a universality is defined as just a synonym for additivity of optimality. So it's not clear. It seems that what they want is to consider the optimal machine, but why they use the word universal, I have no chance yet to ask them, but it's interesting. And also it's interesting for other two main textbooks, which is Downey and Hirschfeld and Nice. And both of them very clearly write that there are so there are two types of requirement. One of is universality, which Downey and Hirschfeld called universal by adjunction. We add the prefix and then imitate any machine we want. And this optimality, which is, as they say, more general notion. And then he says that it's irrelevant in most cases, but we adopt the stronger one, the required universality if needed. But it's not clear for me. The book is very thick, and I cannot find any place when we really need it, why they are so careful about that. And the same thing happens with the Nice paper. And they say that usually it's not important which machine we consider, but if we we want to have some particularly well-behaved optimal machine, and this machine is universal. So it's a bit strange. And again, I don't know, I haven't seen Andreas since then, and I should ask what does he really means here. And there is a mathematical reason. It's a simple fact, but still, I think it's worth mentioning because there is some kind of unclear situation what definition we really should use. And if we are interested in the only the complexity function, then we don't care. So if we have an optimal machine, we can just twist it a bit, making it universal and don't changing the complexity functions. So definitions, there is no constants here. Of course, all the complexity functions differ only bounded by constant additive term. But here there is no constant. We have just the same class of functions. And if you are technical, you want to do this also with conditional and prefix complexity. And here it's unpleasant situation as sometimes it's possible to do, but some cases look suspicious. We don't know whether it's true or not. And so if we look for conditional prefix complexity, we get in trouble. Here, maybe optimality is not the same as universality here, but who knows? Anyway, this is all up to a constant. And of course, there is a more as Yuri said in his comments, practical people are laughing when you say that there is a constant which is several hundreds or several thousands maybe, and all your notions are defined with this kind of precision, and also they are uncomputable, which is another problem. But still it would be nice to have some, to choose, to agree on some specific decompressor, specific programming language, to have something more reasonable. And it was motivation for Levin. He noted that Kolmogorov didn't provide any indication how we should choose this optimal language. And there is an important phrase, we will see it later. In a number of construction, the complexity appears in the exponent of important expressions. So 100 is also unacceptable here. And so this is the problem. And there is some solution, not solution, but some progress suggested by Levin. And he defined very specifically one specific optimal interpreter, optimal programming language. And it should be very, not simple, it should be very economical, very efficient in terms of program length. And this was the claim of Levin, that maybe one can start with this and improve something and get several tens of bits instead of thousands. And of course, it's a very informal claim. And it seems that Levin hoped that it can be somehow developed. But unfortunately, since this paper, I haven't seen any paper which continues this specific approach or prove something or use something. It's kind of dead end up to now. And there is a nice picture which shows another attempt to get an efficient interpreter. So you see that this picture is not that big. You can look at it, and this is first Chaitin tried to do something with Lisp. He wrote at some specific universal programming language based on Lisp, which was not at all compact, but still Chaitin for some reason took the trouble to define specific language and write long programs and even embed the exponential Diophantine equations in this and so on. But at least it was some example of specific programming language, specific results. And John Tromp, who switched from Lisp to more concise combinatorial logic, has defined some specific universal machine and even proved specific theorems. So there is a well-known theorem about complexity, that complexity of pair is bounded by complexity of the first element of the pair and the conditional complexity of the second element and constant. Here's the prefix version, but this doesn't matter much for now. And this specific constant he computed exactly. It was about 2000. So it's still much more than even Kolmogorov thought about the constant. And one can even look from a more practical side. So what is actually this constant? We have some other programming language, and then we want to write a program or interpreter or compiler for this new programming language in our original programming language. How long it should be? This length is just this constant because we need to add this compiler to any programs written in this language, in this compiled language, to translate it into our original language. And this constant is just the size of compiler. And now it looks ridiculous because now every compiler is several hundreds of megabytes or gigabytes or whatever. But if those of you who are old enough remember that the first personal computer appears for children, for schools, they have some compilers for languages like C or Pascal, which fit into the memory, and memory was 32K, and so you need a compiler there and a space to run a program. So there were compilers which took only a few kilobytes. A kilobyte is tens of thousands of kilobits, but still it's not that big compared to the Tromp's efforts. And there is also a very important thing which was considered by many people, and including the paper of Gurevich and Passmore, and why we are interested in the constant. Why it would be nice to have some specific interpreter with small constant for other translations. And this reason is that we can use them for detecting non-randomness. It's actually the main problem of statistics. So we have some experiment, I don't know, testing a drug or something, and want to say that what we observe is not just some random thing, but for example, happens because our drug is better than the previous one. So we need to decide when we should declare something to be non-random. And this is the well-known problem in statistics, which is called p-values. So we make some experiment, and we decide that if we have some null hypothesis, if there is no change no improvement in our drug, or it doesn't act at all, or whatever, then the results we see are, well, of course, they can happen randomly, but according to this null hypothesis. But the probability of the fact that they happen is small. And we should decide when it's small enough so we can publish the paper. And of course, nobody will, if the probability of something is, I don't know, 1/3, it will be ridiculous. Why it often happens. But if it will be 1/2 to the 100, then probably no biological paper using this testing can appear at all, because it's ridiculously low. So for some reason which I don't know, they for many years they have some, and still now probably they have some very important threshold, which is 1/20, 5%. And so they say that then if we see something which has probability 5%, then it's probably not random. It deserves, it makes the paper good and it could be published. And so this is from the viewpoint of theoreticians, this is somehow a philosophical question. If we have a specific object, what does it mean then it is random or it is non-random? And for classical probability theory, it doesn't say anything. For classical probability theory, there is a uniform, for example, for a fair coin, we have a uniform distribution of all possible strings, and all of them are equally probable. So it doesn't make any sense to ask which is more random or which is less random. They are just all equivalent. And but still it's funny, because there is classical probability theory and classical statistics, and classical statistics is exactly the more or less the practical recognition of non-randomness, and still there is a gap, a wide philosophical gap between this theory. And somehow algorithmic information theory tries to clarify something in this gap. So actually, if we see some string x and want to say that it cannot be obtained by a random coin tossing, and this says that actually what we see that, for example, the strings of zeros, why we don't believe that it's random? Because it has a very short description. So there is a notion of randomness deficiency for a fair coin. If we have string x, we compare the length. So how long does it take to specify the string literally, and its complexity. If we use the better way of specifying the string, what is the difference? And it somehow, in terms of statistics, it corresponds to a p-value which is 2 to the minus d, because the probability of this event is more or less 2 to the minus d. And you see here that this is very, very important, which complexity function we take. So, of course, if we do not have any restrictions, that everything will be non-random, because we can choose some complexity function which is adapted to this sequence, and with this specific sequence has a very short description, and so we have a big deficiency, but of course it's cheating. And this is what probably what the Levin had in mind, when he spoke in that this complexity appears in the exponent. So you see that this deficiency d of x appears in the exponent of p-value, and complexity therefore is there. And so if the constant, practical acceptable size of the constants only tens of bits, so 1000 is already quite significant, if we remember that this was just 5% for biologists, but still 100. So this corresponds only to constant 10, and so it seems more or less hopeless, but still. And there is a paper of Yuri Gurevich and Grant Passmore, which tries to somehow bridge this gap between theory and practice. saying that we should consider not the arbitrary descriptions, but description in very specific language, which is chosen for a given domain. So we need to make this choice specific on our domain and agreed in advance. And in this case, a non-random object is something that satisfies a short formula in this language. And this formula is not only short, but also describes an event that has very small probability. And the connection with general approach is that small probability actually, if this formula was chosen after the event, then of course there is some constant, the number of formulas of this or smaller size that can have this property. So if we for some reason know that this formula was given before the event, this statisticians will like this. But if after the event we suggest such a formula, this is kind of freedom, which should be compensated by the number of possible formula. And actually, if we try to translate this approach to our complexity language, it's just our complexity language corresponds to the case when we assume any formulas as descriptions. So if we don't limit the arbitrary choice, which was the original idea, then we just start with general complexity deficiency, randomness deficiency, and then so restriction can help. And now there is probably kind of alternative. It's not from the paper. It's just some speculations of myself based on this paper. This is a kind of alternatives provided by large language models. So complexity is more or less corresponding to something what is called a priori probability. It's not the short, not how short the description is, but how probable is to get this thing at random when using universal machine. And this existing LLMs are kind of a replacement for this universal machine. So they try to predict next token. And so actually they in their internal mechanism, it seems, I don't know much about this, unfortunately, it seems that they somehow estimate this a priori probability based on conditional to what they learned, and what they learned is somehow the previous human knowledge. So if we know for sure that if the machine was trained before the experiment, and then we make an experiment and get a result, then it's safe to say that some simple property is violated if this property is simple according to the previous version of the machine. Now, I don't know whether it makes any practical sense. We have so many different models, and it's not clear to me how much the probabilities generated by these models differs. And it would be very interesting to hear from someone who knows better. So I am just, as everyone in the world, observing this miracle which happens with these machines, but not really understanding how this could happen. Anyway, this is some approach which kindly may be kind of practical. So maybe if you want to use in the court, it's actually a serious problem, because some medical people were it was detected that the frequency of death of the patients was somehow correlated with their appearance, and then because of that they were convicted. And of course this can it be just a coincidence? So the completely innocent people are just convicted because of this, and but still algorithmic information theory is not ready to help the courts to make some laws or decisions on this type, I think. Okay, and there is another things which I will try to speak shortly. So if we return to mathematics from all this disgusting real world, again, there is a place when Kolmogorov complexity, constant in the theorems of Kolmogorov complexity are important. So this is a big part of combinatorics, not important part of combinatorics, when they try to use Kolmogorov complexity as a tool. And there is an entire section of Lee and Vitani book about incompressibility method. The idea is that we want to prove that something exists in the simplest case, and then how do we do it? So we want, for example, we want to prove that a matrix, there is a matrix which doesn't contain a large Boolean matrix, which doesn't contain a large uniform minors. So we cannot select many strings, many columns and many rows in such a way that on the intersection we have only zeros or only ones. And the argument is very simple. Imagine that such a minor exists. So we know some rows and we know some columns, and in the sections are all zeros. So if we want to specify the matrix, we don't need to specify the elements of in these intersections of the rows and columns individually. We just say that all of them are zeros. Of course, what we need to specify are the rows and columns. But if the minor is big, this is still an economy. So if we have minors of size m times m in the matrix of size n times n, then for each row and for each column, we need log n bits. And so we have, if we have m rows and m columns, we have 2m log n bits. And after that, we don't need to specify bits in the intersection. And in the intersection, we have m squared bits. And so if m is bigger than 2 log n, then we get some improvement. And this is, so it shows that random matrices, incompressible matrices, have no minors of size 2 log n plus c. That c is some constant which appears from Kolmogorov complexity, because we have some specific way of describing our matrix, and we should say that it should not be worse than the universal way by some constant. And still, it's a combinatorial statement, so we need. It's strange that we have some constant. There is nothing, no parameter. It should be some specific bound. And in this case, it's very easy. And in many cases which are given in Lee and Vitani, this is really easy. So in this argument, we actually don't need our Kolmogorov complexity. And we don't need this universal description. We just use some specific language which is defined by the specific decoding procedure, and say that our string matrix should be incompressible with respect to this specific language. But still, it's kind of it's kind of confusing. So, for example, if you look at Lee and Vitani book, it shouldn't, what is written there should not be interpreted literally. It's just false, because they write some inequalities without constant, and this is not doesn't work really. And so what I said, for simple cases, we can just use specific u instead of general u, and this is what is happening. But still, not all application of Kolmogorov complexity are that simple in combinatorics. So there is another things. Let me mention briefly a more complicated case, and even more complicated case. The more complicated case is what is called Levin's everywhere complex sequence. So it's sequence that looks more random than a random sequence. What does it mean? That if we take any long substring in the sequence of bits, then its complexity is at most its length. And of course, in a truly random sequence, we have long subsequences of long fragments made only of zeros, and long fragments made only of ones, and this is not true. But if we don't want real randomness, we can make something more random than random. Every substring has high complexity. And this statement has a very easy combination, not easy, the translation is easy. We can translate in the combinatorial language in this way. For every n, we declare some strings of length n as bad strings, and we don't want them to appear as effectors in our sequence. And if we have not so many of them, if we have at most 2 to the 99% of n strings of this length, instead of among all 2 to the n strings, then there is an infinite sequences. There is a Russian book, The Миллиард лет до конца света. And just one part of the plot of this book is that there are some guy working on some important theory. And then he is close to some important discovery. And then the universe makes some looking random actions to prevent this to be discovered. So I don't think this is, but it's funny that first the Lufthansa didn't want to be, and there is a sound. Okay, anyway, so there is a state, some combinatorial statement about avoiding factors, which is can be proven using complexity tools, Levin's lemma. And Levin's argument was not that simple. It used the symmetry of information, so it's not of the simple kind. So if we want to have some specific bound, which would be nice to have, then we can either try to use some explicit constant in the results about complexity, or just to find a reformulation of the proof or other proof which doesn't use the complexity. And there are some ways to do this. And that's another story interesting in itself, because some people for very different reasons found different proofs. And strangely, they give the same bound in many cases. So there should be some hidden secret here. But this is another story. But there is a more complicated case. So I think the time is tight, and it's not very even. That's kind of a game, a combinatorial game in which is somehow related to learning theory. And it turns out that some complexity result obtained by Ramashchenko and Zeeman can be used to prove something about aggregating opinion in learning theory. And this was discovered by Steifer and Kazachinsky. And what is funny from our viewpoint is that I tried to list some of the game, but it doesn't matter really. There is a result upper bound with the main term is square root of t. And if we try to use it to prove it without complexity, we get only weaker result. No, we get, maybe someone else can get full result. It will be very interesting. But still now the only known bound without complexity is worse. And so it's interesting how to get, if we want specific constants in this combinatorial theorem, how to get them. And it's not, there's not really reasonable constants, but of course we can follow Tromp and design a very concise programming language and then use it, and then we get something very large constant. And there is some alternative approach that we do not try to use good programming language, but just see what facts about complexity we need, and then provide some special complexity functions which has smaller constant exactly where we need them. And so in this way, we can replace several thousand by several dozens. So for example, the constant from Tromp can be now made 30 instead of, or even maybe 20 or something like this, but still much better than this several thousand. And this is quite easy if we need some special theorem, for example, that some algorithm doesn't increase complexity by much. And then we just adapt our change our universal or optimal algorithm by allowing the specific operations to be included. So for string starting with 0, we have the previous one, and for string starting with 1, we have this additional application of our specific algorithm. And still it's recursive definition, but it's okay. And we need the same trick, but in more difficult case with cleanly fixed point, with it for the complexity of pairs. But this is another story. I submitted. There was some last moment changes, so it's not yet an archive, but it's submitted there, and I hope will appear soon. And that's all what I wanted to tell. And again, I want to congratulate Yuri, who somehow he spoke several times about the importance of specific constants in Kolmogorov complexity. And this was one of the motivations for trying to think more what can be done and what cannot be done. And I also, my teacher, Vladimir Uspensky and Alexei Semyonov, also insisted that something should be done about fixed constant. So this is a kind of very incomplete, but still a reply to what they asked. And thank you for the attention. And it's very nice to see you all, even only in Zoom version.